Hello everybody, my name is Shaun Bentley. I've been with SOLIDWORKS in general for the last 14 years or so, since 2006. Been specializing in simulation since my start. What I'm here to present to you today is getting started with simulation standards. This is a product many of you may have picked up over the holiday and wanted to know how to get started using it, or maybe some of you had it for a while and never had a chance to try it out. Here's this presentation's for newer users to get started with it. On the agenda, what I plan on covering with you today is, first of all, what is simulation standard? Where does that fall into the list of different simulation tools? So spend a brief moment on that, just setting the stage. Then we'll move into setting up our first simulation study. Now, before I get into just the button clicks of creating loads and fixtures and all that, it'll be worth it to go through and set up a quick simulation template. These templates will save you a lot of time. Then we'll create a simulation study using that template. Then we'll also show another study, a different study that uses some assembly connections. So we'll explore a few different facets of the simulation interface there. And then also we'll look at running a motion analysis, which is also part of your simulation standard. More on that in a moment. So to begin, we'll start with this first topic. What is simulation standard? Now, simulation standard falls into a group of different simulation packages. Simulation standard includes linear static analysis for assemblies, time-based motion, a fatigue calculator, and a trend tracker. And if you compare this simulation standard tool to simulation professional, simulation premium, you can kind of see where it fits in. Sort of our base level, probably the most popular tool to get started with FEA. Linear static and time-based motion, those are going to be the two big topics that I'm going to be covering in this presentation. I'll do a quick fatigue study as well, just to give you a flavor of that, but I do plan on hosting another webinar next month that's going to go over the fatigue in a bit more detail than what I'll have time for in this webinar. So in short, what simulation standard is, on assemblies, it allows you to analyze a wide range of stress and deformation problems, and also to analyze motion dynamics and kinematics. It's really those two core tools that I circled. So now let's get into the software next, and we're going to go through setting up a simulation study, starting off with creating a simulation template. Now, out of the box, your simulation standard, when you run a structural analysis study, it's going to look something like this out of the box. You see the color chart, a lot of scientific notation. Units are very tiny, newtons per meter squared. So what we're going to do out of the box is customize some of these result templates, let's call them, so they look a little cleaner. Okay? Something you may want to do on your machine before you even get started with your first simulation study. So here you can see same kind of stress levels, but just different chart scale, just cleaned it up. And also the color chart itself, the actual default out of the box color scale, you can just see there's a big green region here for the default one, which I can't really tell the difference between this color here and like that one there. They look about the same to me. Versus we have this one called optimized for color blindness. We'll change it over to. That's, I think, a little more broken up, and it'll be better for use in your presentations as well if you use a scale like this. So if you have anybody you're presenting to that's red-green colorblind, or this might break it up a little better for them. Now, where do you even go to change the template? It's going to be in our simulation drop-down under options. We're going to go into those default options to make some of these changes. Let's get started with that. Here we're in our SOLIDWORKS CAD environment. In order to change my simulation template before I even run any studies, first I'm going to enable our simulation add-in. Now, since I have a network license installed on my machine, you see I have a little drop-down arrow for my SOLIDWORKS add-ins where I can turn on different levels of SOLIDWORKS simulation. Now, you might just see a button there without the down arrow. And in that case, you just click the button. It would pull whatever license you have access to. But in this case, since I have all these different licenses, I'm just going to pull a seat of simulation standard off of my network. So if I go ahead and click on that, you'll see a couple of interface items will get added to my SOLIDWORKS. First of all, right in the top, you see a simulation drop-down gets added on, and also a simulation tab gets added to the command manager. That lets me know that it's booted up the simulation tool. And now we're ready to make some changes to our simulation template, which is right up here. If I go to the simulation drop-down under options. And in here, If I go under the default options, some of the things I'll change for this presentation are things like I'll use English units a lot here. And instead of PSI, I'll change over to KSI. It just makes the, instead of reading 90,000 PSI all the time, it'll just say 90. And also, if I go under color chart, we can make some adjustments to that color chart like that. Instead of that default, I'll use the optimize for color blindness, breaks up the scale a little better. And then instead of scientific notation, I'll change this to general and use floating points for stresses and factor safety plots. They recommend this. And also for the general ones, we'll bump those up to a few extra decimals. I like to see, even though if the simulation accuracy doesn't entirely justify 5 decimal place accuracy, I'd like to see a few extra decimals sometimes. But those are a few of the key customizations. You can adjust a lot of other things about your simulation template in here as well, but I'll leave it at that. Once you're all done making those customizations, you can click OK to that. Okay, so that's taking care of our template. But now let's get into setting up our first simulation study of the day. So what we're going to be doing in our first study is we've got this elliptical machine that we need to analyze. Exercise equipment's great for demonstration purposes because I think everybody get the concept of where the loads are coming from and so on. And in this case, we're going to look at the stresses that build up in this arm right here. And so you can picture when you're moving, if you've ever used elliptical, you're moving up and down, it's creating a load on this, maybe going left and right, back and forth, and it's going to be bending this arm. Now, in our case, our model looks a little different than this one I got off of some manufacturer's website. Our model looks a little more simplified. You can see that we have our link arm here. So what do I do if I want to set up a study on this? What do I do? Do I model this entire assembly? Do we model all of this? And do we even put do we put a person on the top here and or like just some sort of weight, or do we put forces here and then see what happens to that little arm? Do I analyze this whole structure? Well, that's what unfortunately I see a lot of people end up doing with their first studies, is they try to take a bite out of the whole elephant rather than one little piece at a time. So here, if you were to start with a full complex assembly, a lot of times the path to your goal or to success, it winds up looking a little bit like this, where you kind of start down the path and then you bump into a bunch of error messages when you try to run the study. It doesn't work and you have to backtrack. Maybe you start down a different direction, kind of parallel to where you're going, and try it again and still can't get anywhere, and you end up giving up after a while because if you just keep trying to hammer away at this complex model, it's hard to get anywhere. So generally your approach for your first studies, if you really want to get started using the tools, is start simple. Okay? Start with this relatively simple version of the model. In this case, only maybe a couple parts, maybe even a single part to start with. The simulation will be a lot easier to run on that. Okay, you might still struggle a little bit, backtrack, and then you can scale up as you have success with those simple parts. You can scale it up to more and more complex things and run those and see if it makes a difference. As you add more components and you see it's not making a difference to your actual stress result, well then you've reached your goal early without having to run that full complex assembly. So this is the type of approach we're going to take. We're going to start with a model that looks something like this, and then we'll also run we'll take one step further. We'll run a model like this and we'll compare the results and see if we get about the same answer. To get started, we're going to create a new study to analyze the stresses on this arm. The kind of load case I'm going to be testing here, we're going to be putting 300 pounds. Okay, that's what I'm estimating. When we stand on the elliptical, it creates this 300-pound load. Maybe that came from some hand calcs or a motion study. I imagine 300 pounds put on this arm here. And I'm going to fix the belt location so that we can see the net torque that it's going to create on the arm. And then we'll do this, like I said, those two different ways, starting out with a simple just two-part assembly and then adding more components to it. I'll go ahead and create a new study. This will be a static study. Okay, and you can kind of see simulation standard. See how it grays out a lot of the other study types. We just have the static and the fatigue in here. But I'm going to create a static study, and I'll just leave the name static 1 for now. And once I create that study, you can see my SOLIDWORKS tree is now broken up into two pieces here. You can see here's my SOLIDWORKS tree here, my modeling tree, and then here's my simulation tree. So the idea is you could go up to your SOLIDWORKS modeling tree and make a change and then rerun your simulation. Go up here, make another change, rerun your simulations. It's nice having them fully integrated into one another like that. We're going to walk through this simulation tree pretty much just from top to bottom. You can go in whatever order you really want in the tree, but I'm going to go from top to bottom. Now, by the way, if you did want to follow along with anything I'm doing, these models, they're tutorial models. Okay? I'm not going to follow the tutorial steps per se to a T, but if I go up to that help pull down under tutorials, okay, and your help pull down might be over here, it just depends on what version you have. If you go under tutorials, you have your simulation tutorials in here, and you'll see one of them looks familiar, this analysis of an assembly tutorial. And later on there'll be a motion one, the SOLIDWORKS motion tutorial we'll look at. Okay, and one for bolt connectors. Okay, so you can kind of see we're going to use that one later too. Okay, so all the models I'll be using here, you'll have access to if you want to play with them. They're all in these tutorials. But what we're going to do, I'm going to pretty much walk through this tree from top to bottom. Start off with this parts folder. And in the parts folder, you can see some of these bodies already have a material on them. Two of them do. This one here, axle, has this little SW alloy steel on it. The SW means that it pulled the material from SOLIDWORKS. It knew that I assigned the material to the SOLIDWORKS CAD, so it copied it automatically over into my simulation for me. But then there's these two that are missing material because I didn't assign them to the SOLIDWORKS CAD. So let me go ahead and take care of these two crank arms. If I go ahead and right click on either one of them and apply material, and you can group select by the way, but I just want to show you something kind of nifty here. If I right click on one of them and apply material, I'll select the alloy steel in my database. Okay, a lot of other materials in here too. Steel, it's basically just using your same SOLIDWORKS material library. I'm going to go ahead and grab our alloy steel and apply that. And close the database. So now there you go. Puts a little green check mark on that crank arm. And if I want to copy that material, I can actually just drag crank arm 1 and drop it onto crank arm 2. It's a little trick. Okay, drag and drop to copy. By the way, that drag and drop to copy works in a lot of different ways. You can drag and drop meshes from other studies to copy them. Alright, so there, I've got all my materials applied, but really I want to do a simulation not on all 4 of these. I want to start simpler than that even. So I'm actually going to exclude these two guys. Okay, this crank arm and then this wheel. So if I go ahead and select these two bodies in my simulation tree, I have an option to exclude them from the analysis. And now I'm just down to just the simpler version of my crank. So now what I like to do, move past the parts folder. Now let's take a look at how these two parts interact with each other. You can see that looks like they have a keyway and everything in here, and they're kind of touching. The SOLIDWORKS resolution is a little choppy, so it looks like a decagon or something in there, but they're circular faces. So what do I want to have happen there? By default, SOLIDWORKS simulation is going to try to bond together any touching faces. That's what this global interaction is in here for. It's going to automatically try to bond together touching faces. It does that by default with every new study that you create that has more than one body in it. It's going to try to bond together touching faces by default. Now, do I want it to do that here? Well, if I don't care about the stresses here so much, if I don't care about some of the local stresses that might be on this keyway, maybe this is okay. I'm going to try it for our first study, and then we're going to change it a little bit later on, see how big of a difference it makes. But I'm going to try bonding that stuff together. Now, do these faces touch? Well, we can check. You can use a tool to check and see if they touch. Right up here on the Evaluate tab, you have the old interference detection tool. Very handy. I use this tool a lot for running simulations. And if I go ahead and just use this tool to calculate for interferences, it says, hey, there's no interferences. Well, that's good. But really, I want to treat coincidence as interference and then calculate again. And now it says, oh, well, you do have a couple coincidences. These are regions where they touch. These surfaces touch one another. So that tells me, this tool is telling me, these are going to get bonded together by default. Which, okay, I'm okay with that. I'm going to go ahead and cancel that. And I'll refresh the view. Whenever you run that interference checker tool, those excluded components, they're still excluded, but graphically they reappear. But down here, if I go back to my model tab and then back to my study, it'll refresh the graphics. So a little quirk of that tool. So now let's move on to our fixtures and our loads. For my fixtures, you can see here, that's convenient that I have a face right here that I can maybe fix. Normally this would be just one long face, but it looks like it's been split up into 3 separate faces for me. Well, this is actually something I created. I created something called a split line, so I have a nice face here that I can fix. And this is something that you'll need to know how to do likely for your simulations. So let me make sure we're on the same page there. I'm going to show you creating a quick split line. How do you create this type of thing? If I open up this part, it should be in a part modeling mode of some kind, either editing a part in assembly or open up the part. If I open up this part, and in this part, what I can do is I'll add a sketch onto, you kind of see this plane here, I'll add a sketch onto plane 2, just for demonstration. And maybe I'll draw a sketch that looks something like that. Okay. Pretty similar to what I drew over here, by the way, for this split line. But I'll draw a sketch that looks something like that. And what I'm going to do with that sketch is I'm going to project that sketch onto this big cylindrical face here. You'll see what it creates. So in order to do that, we have to use this tool, Insert Curve Split Line. Okay. It's probably the hardest part of the tool is remembering that it's located here under Insert Curve. You can do command searches for it if you forget. Okay, right up here, Insert Curve Split Line. And now I'm going to take our current sketch and I'm going to project it, you see projection here, onto this face. And then I'll click OK. And there we go. Okay, see how it breaks that up into 3 separate faces now. Now I don't want that to actually be split there, so I'm going to get rid of that split line. Okay, I'm just going to delete it off here. But that's how you create one. Okay, you just draw a sketch and you can project it onto your faces. Let's go back to our assembly. Continue where we left off here. So I've got my split line on there already for me. Let me go ahead and fix that face. So I'm going to right click on my fixtures and go under my fixed geometry and say that face is not allowed to move. Okay, while we push on this, we're going to see this thing twist while that one is not moving. And I'll hit OK to that. And now, up here is where I want to place our load, so I'm going to create a force, and I'll plop a force onto that face. Now you can see the default directions. It tries to go normal. That's why this is, it says normal right here. It tries to go, it's like it's trying to crush the face or something. But I want it to go in like the X direction or something, or really the negative X. So how do we get it to do that? You're going to use this selected direction tool a lot. Okay, you're going to switch over to selected direction, and that way you can pick a reference. Things like an axis, a straight edge, even a cylinder, okay, or a plane, or a sketched line. That's another popular choice. You can draw a line in the direction you want this to go and then click on the line. In my case, a nice reference I think would be, here's a plane. Plane 3 looks like a good choice. Okay, because you picture if I go normal to that plane, then we'll be in good shape. So I'm going to go ahead and click on this normal to button. You see when I hover my cursor over, it says normal to plane. Gives me that little feedback. So we try to keep it easy so you know which way is which. And then I'll key in our load magnitude. I was estimating we're going to try out 300 pounds on that thing. And I'm going to reverse it. Make sure it's pointed that way. All right. Looks good. Click OK to that one. So real easy so far. And let's go ahead and create our mesh. That appears to be the next step. This thing called a mesh. If I right click on mesh and create a mesh, I'm just going to leave the defaults here. I'm not going to change anything for this first day. Let's just see what this looks like. Okay, and then we'll explain what it's about. So if I'm just going to go ahead and hit OK to that. And here's my mesh. Okay, breaks this thing up into like little triangles, technically tetrahedrons, little triangular pyramids. The basic idea is that we mathematically know exactly how the tetrahedron will behave when we put load on it. It's a very simple shape that we can mathematically determine what's happening with. And so if we add together all these simple shapes, we can get our analysis results on more complex shapes by using simple shapes like these triangles or tetrahedrons. Okay. Now, another principle behind this meshing that we'll look at in a moment is, especially down here, we're going to look at making refinements to our mesh, applying something called a mesh control to make these triangles smaller, give us better resolution, better accuracy, but also longer run times. Okay, but we'll look at that in a moment. Let me go ahead and run this study as is, where it's going to bond all that stuff together. The run button right up there is my favorite place to click on it. And we get a result almost instantly because it's such a simple model. If I go to my solver messages, it says it took 2 seconds to run that. I can see the results here. Are they bad? Are they good? What's the deal? Well, one way to look at your results is to compare the stresses to the yield strength of the material. Now, what is the yield strength of this alloy steel that I selected? If I go into that material database, and maybe I'll change units here too, I can see the yield strength is about 90,000 psi, or in other words 90 ksi, 90 kilopounds per square inch. So 90 is the number. And how are we doing? 23. Seems like that's the peak anyway, and that might be on a little point here, but really I should probably play with this number a little bit. If I click on that top number and I change it to 90, you know, we're looking pretty good. Okay, I don't see any, doesn't seem like we're that close to the yield. Okay, see a little color down there. But I change it to something more like maybe 10 or 12 or something. That gives us a little better idea how the stress flows through the bracket. It's nice to see more color, so we can see what's really going on with it. Where is it stressed? Okay, but it seems to me like we have a decent margin, decent factor of safety, somewhere in the ballpark of a 3, 4, 5, somewhere in that range, if we're looking kind of more at general stresses, or maybe bigger. But yeah, looking pretty good so far is my interpretation. Then also take a quick look at displacements. How much did it twist overall? About, according to this, about 30 thousandths. Okay, I'm going to compare that to our next one, about 30 thousandths, and stresses in the neighborhood of 12 in some of those regions. What I'd like to do next, let's run a better study. Let's add a little more to this and see if we get the same answer. So what I'm going to do is down here, this is where it stores all the studies we've created so far, which is just the one. See static 1 down here. If I go ahead and copy that study, and I don't know, I'll call it static 2. Very creative. You may want to use more descriptive names for your application, but anyway, I'll go ahead and hit OK to that. Okay, so now I got static 2, which is a direct copy of 1. And what we'll do in this study is I'm going to re-add those couple of components back in here, re-include them. And we're going to mesh those components, and we're going to see these components twist a little bit too, like this wheel and everything. And I'm going to move this fixture though. This fixture used to be there, but now that I'm modeling this geometry, I'm going to move that fixture somewhere else. So I'm going to clear that face off of that fixture. I'm going to move that fixture maybe way out here. It's kind of like that belt's not moving for a moment, and I'm cranking on my elliptical machine, and I want to make sure this arm doesn't break if I do that. So I'm going to fix out here where that belt's located. And now let's see what kind of stresses we get. Are they going to be any different? So I'm just going to go ahead and just click run. It'll automatically remesh the model. It'll use the same settings that I had before for the mesh, but it'll remesh it, and then it'll run it. Instead of 2 seconds, now it takes 7, 8, about 8 seconds to look like, almost 4 times longer to run. It's quite a bit more volume that we're meshing, so makes sense it would take a bit longer. But did it make a difference for me including those extra components? Do you see 0 to 12, same units here? It looks about the same to me. Okay, what about displacements? Do you remember the result we got for displacement? 0.03. It was 30 thousandths before, but now that's changed. Now it's closer to 36 thousandths, 0.036, let's call it. And that makes sense that would change because now we are accounting for extra bending and deformation on the wheel. And if I want to, you can kind of see the results, how it looks like it twists a bit. If I want to exaggerate this further, just to see what's happening to the wheel, if I go up here, this deformation scale, which is exaggerating by about 43 times. If I go up here and double click, I can change that up to, I don't know, let me do 200, exaggerated by a factor of 200. And now you'll see some weird behavior here, but ignoring that, if I just animate the displacement, I just want to look at the wheel and see, yeah, it is twisting a little bit. That's contributing to that little extra displacement that we saw of 0.3 we had 0.03 before, and then we had 0.036 this time. All right, now I'm going to go and scale that back down to a little bit closer to reality here. Just to be sure, I'm kind of relying on my memory a little bit to compare the results. So maybe what would be nice to do is put this stress result side by side with the result I had before. Maybe take a couple screenshots or something. Or we have a compare tool that will make that easier for you. If I right click on the stress plot and then use compare results. Here what I can do is compare across all studies in this configuration. I'll grab just our two stress plots from the two different studies, from static 1 and static 2. It's a real easy tool. Just hit OK to that. And there we go. And they're linked together too. If I zoom in this guy, and if I zoom in the top, the bottom one zooms as well. It's kind of nifty, but there I can see. I'm looking at the top, looking at the bottom. It looks identical. Like even down to like the way the mesh creates a little bit of spottiness. Even that seems to match like exactly. So to me, it says it helps me to build confidence in the very first result I got, to see that when I added more detail, I get about the same answer. So here was our comparison that we just looked at. Looked like we got about the same answer when we added more detail. But what I like to look at next is, what if we model this joint a little more accurately? Now, I'm not going to model in little grooves and everything in detail, but I just want to give you a sense of if we add a little bit of additional accuracy to the way we're modeling this joint, which right now we're bonding together. I'll remind you, we're just bonding it together like there's some sort of glue in there holding them together. What if we instead model them with what we call contact, like a sliding contact with some friction? What I'd like to do is I'm going to go back to our first study. I'm going to make another copy of this first study, because it seems like the wheel doesn't matter all that much, so I'm going to exclude that from my subsequent studies for now. Okay, so I'm going to go ahead and make a copy of our static 1 study from earlier. Okay. And maybe, sure, I'll give this one a nice name, contact, because we're going to use sliding contact. And in this study, pretty much all we're going to do is I'm going to go in here, and where it's bonding things together, where we have this bonded contact in here, I'm going to change that. We're going to edit that so that it doesn't bond stuff together. We're going to change it so there's contact. Okay. Now, by the way, if some of you were familiar with older versions of SOLIDWORKS simulation, if some of you had used 2020 and 2019, they changed the names of stuff here. You might have remembered this used to be called no penetration. Now they're calling it just contact. And the word where they used to use the word contact, where up here it used to be called component contact, they changed that word to interaction. So just watch out for you if you've been using for simulation for a while there. They've changed the name, and you get used to these new names. I think I do prefer them over the long no penetration contact. Anyway, so we're going to change it to the sliding type of contact, and I'm going to use a coefficient of friction, and I'll use this default coefficient, just something small that will keep things relatively stable. Now, generally I recommend that we maybe start off studies without it, and maybe use some other techniques to restrain things, but maybe I'll be a little bit lazy here and I'll just turn it on and cross my fingers. But we'll try it with some friction. Let's see how that behaves. Okay. And when I hit OK to this, it says, hey buddy, you got to remesh after you do this, because if you ever change the context, a lot of times that will influence the mesh. So it's just warning me that I may need to remesh after making that change. Now, another thing I'm going to do is, I'm not too satisfied with the way the mesh looks in this region, because I know I'm going to start seeing some big stresses on this keyway because we're twisting it, and so I want to refine the mesh around this little keyway. So what I'm going to do there is I'm going to explode the view, a really handy SOLIDWORKS tool to help me set up little contacts and mesh controls. I'm going to use the SOLIDWORKS explode view in order to dig in here and apply mesh controls. Okay, using your mesher, I can apply these little mesh controls and tell it I want the mesh to be finer here, and I want it to be finer here. Okay, and we're going to tell the mesh there to be, I don't know, how about 0.05? I really don't know what size I want yet until I mesh it, or maybe if I measured that, I'd probably have a better idea. But I'm gonna key in this number and look at the mesh and see if I think it'll be good enough. It's a bit of an art. Anyway, I'll do 0.05 for those, and then I'll do another mesh control onto these faces too, because there's a lot of contact there, and I'll make that a little bigger, 0.1. So let's see what that looks like. I'm going to go ahead and create a new mesh. And, you know, I look at it and a lot better than it was before. Maybe could use a few extra elements if you really want it, but let's, for demonstration purposes, we'll keep it to that. And I'll go ahead and collapse the view for now, I guess. Maybe I'll re-explode it later on once again, but let's just see how that all looks back together there. And now we are ready to go on this one. I'm going to go ahead and kick it off, hit run. And now remember, this study used to take 2 seconds to run, and now it's already tripled that time. Remember when we bonded things together, it only took 2 seconds on these two parts? Now it's 12 seconds, 13, so on. It keeps going. Okay, well, that's going. Let me see. Quick question: does SOLIDWORKS have polyhedral mesh option? No, our meshers. A lot of CAD-based simulation tools. We try to keep it really simple so that the designer and the engineer doesn't have to worry about creating this type of mesh, that type of mesh. Okay, we try to keep it really simple. The only elements that we use are, for solids anyway, are pretty much tetrahedrons. For those guys who are a little more technical with it, we have Tet 4s and Tet 10s, what we call draft quality and high quality elements. We do also have shell elements for surface bodies and beam elements. Thermo deformation simulations? Yes, yeah, you can include temperature loads, okay, and have things expand and compress. So we just ran that study, and you saw that one took a lot longer than the last one. 56 seconds instead of 2 seconds, just by me changing it to contact with friction. Okay, that friction also added some time to it too. I think if I ran this without the friction, it's something like 45 seconds. So sometimes that friction can make a huge additional jump in it. So if you bond things together, it really simplifies things. If you can get away with bonding stuff together to get to the result that you're looking for, that really makes it efficient to run your analysis. If you have to use contact, be prepared to wait, especially with a big assembly. It can take a long time to run if you're doing some big stuff with it. So just kind of ease into it. So when you're getting started, I'm recommended here basically is start with bonded contact, and then kind of build your way up to using. I shouldn't be calling it I shouldn't be using the word contact, because they change. Start with a bonded interaction, and then when you start to scale things up, then you might switch it over to a contact interaction, sliding type of contact interaction. Okay. So I've run that study, and do we see different results? Do you remember what it looked like before? It's quite a bit different. Let me show you. I already did the comparison. I got a slide that'll show. Okay. There you go. So here's what it looked like when we just bonded them before versus when I turned on contact. Okay, bonded interaction at the top, contact in the bottom. But now notice, it still didn't make a difference up here. Same stresses up here. It's really just locally it made the difference. So if you don't care about, if you know the keyway is fine and it'll last, it's not going to have any issues, then okay, just bond them together there and move on. Get results where you care about them. But if that's going to be a focus of the study, we do need to model that region more accurately. As a bonus, what I'd like to do is just show you a quick fatigue study, just to kind of basically show you the steps. I'm not going to get into too much discussion with it. So for fatigue, what I'd like to do is take this analysis one step further, and let me refresh this plot here. Because if I look at the stress levels here, it looks bad, it looks terrible, but really I should change the chart, bump this chart up to 90 again. I can see that the stresses, they're not as bad as I thought, okay, but they seem to be the worst case stresses in my model though. Yeah, that seems to be the largest stresses. So, but they do appear to be under the yield strength. Looks like we have a safety factor of about 2, I would guess, somewhere in that ballpark, seeing the yellow here. But does that mean that it's going to last a lot of cycles if we cycle this thing? Maybe I'm going to get a crack that develops there and grows. So we have a fatigue calculator that's going to take into account cyclic loading. It's going to compare our stress result to an SN curve. So let's show that part of simulation standard, this fatigue calculator. So I go ahead and create another study, a fatigue study, using a constant amplitude loading. And what I'll do in this study is I'll add, you see the tree for this, pretty short, just need to add an event. And here's where you add the static study that we ran. That contact static study that I ran is the one I want to add to this fatigue. And basically I'm going to say, take the stresses from that contact study and cycle them 100,000 times. And once I do that, I also need to enter in an SN curve that it can use to compare to. Okay, so I'm going to go and apply fatigue data to all bodies, all the structures in here. And some materials come with an SN curve, some don't. So I think we have about, in the materiality database, there's between 50 to 100 materials that have SN curves already there for you that you can plug in. These are material curves. But in this case, let's just see if I derive a material curve for my steel material that I'm using here. We have ability to derive it for austenitic and carbon steel. So I'm just going to use this first option here for now. And now, so I've applied that curve. And now if I go and run this study, so what's going to go through is it's going to calculate the contact stresses, which normally, if those stresses were up to date, somehow they got out of date, maybe it's me collapsing and exploding it or something. But if those results were up to date, it wouldn't need to rerun that study. Right now it's rerunning it, so I do have to wait that minute once again here. Let's see. Well, looking at other questions here, I saw a couple more pop up. Can you show the forces in the key so we can decide if we should use a bigger one? Forces in the key. The forces. I did 300 pounds. Is that what you're asking, Eric? It's a 300-pound force, and the recording will be available. We'll post it to YouTube. Let's see. Oh, the forces in the key. I see. Like the stresses or something, or you want to see the contact forces? Okay, we can. I'll take a look at that in a moment. All right. But now let's rerun that study. Now I can look at the damage. So if I do this, let me expand this exploded view here for you. And customize my damage plot to look at 0 to 100%. So here, 100% damage regions, that tells me 100% damage, that means that it went over the curve. So whatever curve I applied, it's gone over it. Okay, that usually means that that curve is usually based on a test specimen that has a certain number of cycles that it can last at different stress levels. And this is saying that if I had that test specimen at that same stress levels that this is at, that specimen would have broke. Okay, it would have fatigued. And so this seems to imply that we may have a fatigue issue here. We are over 100% in a pretty big region. Okay. Okay, net force. Oh, okay. Yeah. Question on the contact forces. So if I break those up, if we're curious about the contact forces here, if I go to list result force, going back to my static study to look at the contact forces, I got this contact force tool, and I can select primarily this face here. If I update it, it says it's got a force of 3,400 pounds on it. 3,400 pounds. So if that's what you're looking for, so you can just, if you want to apply like a uniform load to it perhaps and try to reproduce it, you could do that. Or if you just want to look at the shear load acting on it. So 3,400 pounds acting on that face. Okay. Next, what I like to do, let's go back to where we were here. So I gave you a little bonus here, just showed you a quick fatigue calculator. Some of the steps we're revolving around it anyway without too much discussion yet. Again, there'll be a webinar next month where I'll go into that in a bit more detail. Okay, saw some damage numbers. Okay, pretty big. So now what I like to do next is we're going to move on to some assembly connections. We're going to do another static study, but this time we're going to use some assembly connectors. Specifically, another tutorial model, this basketball hoop. We're going to use bolt connectors to connect the back of this hoop to the backboard. Okay, and I want to see what happens to these bolts. Okay, do these bolts pass or fail? Which ones get the most load? That kind of thing. So our bolt connector tool, it's going to give us a nice pass-fail red-green. Already kind of giving away the answer here, but we're going to take a look at this red-green pass-fail check tool. So let me go to this model. So in this model, I've already got it partially set up. Okay, I've got this study that I've partially created that has all it has on there is the fixture. Okay, I got a little split face on there for us to fix that face. And it's got a load over here. Okay, force of about twice my body weight. You know, if you want to simulate kind of a dynamic load, so a lot of times what we might do is multiply by a factor, or you might run a dynamic study, but we can't do that necessarily at Sim Standard. Okay, so I've just taken a load that's a little too big in a way, 360 pounds. I'm just going to hang on the end of there statically. And we're going to see what happens with these bolts. Now I haven't modeled the bolts yet, that's all I've modeled so far, was just the fixture and the load. What I'm going to do first is I'm going to use that default bonded contact just to get a quick result and see what kind of results I get. If I go ahead and run this study with just a coarse mesh, just to keep things pretty quick. Of course, it only takes a few seconds, about 3, 4, 5 seconds. And I get a rough idea what the stresses are in the hoop itself. Kind of see the high stress points and maybe want to do some fatigue calculations and that kind of thing. But really, I don't want to connect these two bodies just through a bonded contact. Okay, right now it's bonding those big faces together. Instead, I want the stress to travel through those bolts. So we want to create some bolt connectors to connect these two pieces together. So what I'm going to do instead of bonding things together is I'm going to delete this contact out of here, because I'm going to manually create my own contact. Okay, show you creating at least one local contact. So after I delete that contact out of there, I hit OK to like 3 messages that the developers throw at me. And then now what I'm going to do is we're going to put bolt connectors in their place. So I'm going to use the old bolt connector here. If you right click on your connections folder, you find your bolt connector. And now this is a really handy tool. What we're going to do is I'm going to select the circular edge of the bolt head, the circular edge where the bolt nut's supposed to be. Okay, so the head might go here. And as soon as I make that selection, let me show that again. As soon as I make that selection, a couple things happen. Okay. Let me go back in here. So here I'm on the default. You see 0, 0 right here and here, right? So as soon as I make this selection, it automatically fills out a head diameter and a shank diameter. Okay. It takes whatever this diameter is, plugs that in here, and it adds 50% of it for the head diameter. So you may want to change the numbers and make them more accurate for the actual bolt that's there. Okay, because it does something pretty simple there. But now I'm gonna select where the nut would be, somewhere over here. And moving down, I'm gonna include material for the bolt, alloy steel. It tells it how stiff the bar element. It's gonna create a little beam element going through the center there automatically for me. It's gonna tell it how stiff that bar should be. You know, when we pull on it, it's gonna have a certain stiffness to it. I'm also gonna key in some strength data. Under strength data, I'm going to key in 13 threads per inch. So by keying that in, that'll make an adjustment to the nominal diameter that it's going to use for the calculation. If I key in some coarse threads per inch, you can see that the diameter of the bolt is smaller than if I key in a fine thread. So by keying this number, it makes an adjustment to that shank area. So it makes the hand calculation more accurate. 13 threads an inch. And then also I'm going to key in a torque preload of 60 pound-inches. Okay, it's about, 5 foot-pounds of torque. That'll generate, if I do the hand calc, that'll generate about 860 pounds of axial force. That's a compressive force that's going to hold these, try to hold these two plates together at each bolt. It's going to be about 860 pounds. All right. And that'll be it for that first bolt. Now I got to repeat this 3 more times, so I'm going to turn on this little push pin up here, and then I'm going to hit OK once. And then now to repeat that step, all I need to do is click right click, click right click. There's that bolt. Move on to the next one. Click right click, click right click, and finally click right click, click right click. So you can see the interface. There's some interface shortcuts you can use to make it quick to add those 4 bolts in there. A couple other ways you can do it. If you do a whole series, it'll automatically pattern the bolt to all the other holes without me having to do. So if you created 100 holes and all as a whole series, this would automatically got patterned all those holes for me. I wouldn't have had to create them in all individually like this. But it does have to be a whole series. Remember, I deleted that contact, so right now these 2 parts can go through one another. So I need to add a sliding contact between these surfaces. So once again, I'm going to do that explode view. I've already got one I created. So I'm going to go ahead and use that explode view. And pay no mind to the preview symbols. They get a little funny when you do explode views. But if I go ahead and do a contacts, a local interaction, still use those old names in my mind, but if I do a local interaction and pick, okay, tell it that this face is not allowed to go through that face. Okay, they slide relative to each other, but they don't go through each other. You can turn on friction and all that if you want. Anyway, I'll go ahead and accept that. And that's pretty much it for the setup of that guy. We got our bolts in there, we got our contact, and our load and all that stuff's already on here. So I'm going to go ahead and run this simulation. Now I am using a fairly coarse mesh on this one. While this one's going, again, it's a good chance to take a look at, see what kind of questions we've got popping up. Yeah, got it. You plot stress on a specific face. How do you plot stresses on a specific face or set of faces? If I edit the stress plot, there'll be an option under Advanced Options where you can say, it says plot on selected entities, plot on only selected entities. So you just got to right click on one of your stress plots and edit the definition. It'll be one of those headings there. Are there different mathematical methods that SOLIDWORKS can perform to solve FEA, and are those an option to use? Well, if you trying to think of what the application might be, but we do have CFD for fluid dynamics. Are you asking if we can if we can use boundary element method for or finite volume method for structural problems? So if that's what you're asking, the answer is that is no. We got all our structural analysis problems use the finite element method. Okay, including in our plastics, by the way, SOLIDWORKS plastics. But if you do use our flow simulation for fluid dynamics, that uses the finite volume method. Not related example at hand, but is there a way to... this one's taking a little longer here. What solver are we using here? Now it's Intel. Okay. I might coarsen the mesh up a pinch here, but I guess we still got a couple. There we go. All right, that one's done, but I'll get back. Not related example at hand, but is there any way SOLIDWORKS simulation to dictate element type for example? No, we don't use quad elements. We don't use hex. They're all tetrahedrons. Tet 4s, tet 10s for tetrahedrons, and triangles are tria 4s, tria 6s. Okay, for those of you guys a little more technical with it, but basically they're triangles and tetrahedrons, and then beams. There's several different types of beam elements in the software. SOLIDWORKS does not support hex elements. Thank you, Eric. You got it. Now, I ran this study and I get this message when it completed. I get this message that says, "Hey, there are big displacements on this model." This is a very important message, or rather, it's very common. This is probably the most common error message that you'll probably see running your static analyses, and almost always, I want you to hit no to this. Okay, you can see the options here. Say click yes to solve a large displacement, which means it's going to rerun it from the beginning with large displacement turned on. Or if I click no, it'll present the small displacement result to me. It's already solved it. It says it'll solve, but it's already solved the small displacement for me. If I hit no, it'll present that result to me, and then I can decide for myself whether or not I want to rerun it with large displacement. So I'm telling you, if you didn't expect to see this message, almost always hit no to it. Okay, because if you hit yes, you might be waiting for hours for it to just give you a solver failed message and tell you nothing. Okay, so just hit no to that message if you see it by default. All right, and now I get a result, like I said, almost instantly after I hit that message. I can see my stresses like I saw before. But now what I really want to look at is the results on these bolts. I created these bolts for that reason. I'm going to right click on my results folder, and I've got this tool here to find a pin bolt check plot. And if I Just hit OK to the title of that. Here it highlights in red and green. Pass, fail. Apologize if you're red, green, colorblind, but if you are, you do have this needs attention versus OK, where you can click on them individually. See what those results look like. Here, if I click on this bolt here, you see it highlights this lower one, says a calculated factor of safety of about 1.7, and we are shooting for 2, so that's why it shows it in red. About the same over there. Okay. Why isn't it exactly symmetrical? Why don't we get exactly the same? This is simulation. It's going to be approximate. Okay, and then here 2.27 in the top, 2.28 somewhere in that bolt, 2.29 I guess, somewhere in that bolt. So those seem to be okay. Okay, so it seems like the bottom ones get more stress for some reason, more shear load. And if I look at, you can actually look at the loads on them and do your own hand calculations based on the loads that we calculated. Okay, if you don't like the NASA-based calculation that we're doing, some sort of NASA bolt guide that we're using, you can come up with your own. Use these loads, plug them in. Shear forces on each bolt, axial force, and so on. By the way, so if I ran it with even a finer mesh, get about the same result. By the way, I could probably get away with fairly coarse mesh for those bolt connectors. But here's another result. If I actually model the bolts, which is something that I wouldn't really recommend, especially for new users too, in static study. And this can take hours to run, this level of analysis where you're actually physically modeling the bolts and applying friction and contact and all that. Okay, but just want to give you a sense that if I really exaggerate the deformation, why is a lot of those stresses going to the bottom bolt? You can kind of see the way these things bend, and you end up seeing more shear in this bottom bolt. Okay, so this is more direct modeling, not what we just covered. This is not what we just covered in a moment. I'm just showing you a higher level of detail where you could potentially take it, but generally not recommended to go this high. All right, so finally, our last part of our presentation, we're going to talk a little bit more, changing topics now. We're going to talk about motion analysis. Also part of your simulation standard sheet, we're going to run a quick motion study and show you what that tool is about. So the example we're going to look at here, another tutorial example, it's the SOLIDWORKS motion tutorial. Okay. However, again, I'm tweaking some of the steps around a little bit. But basic premise is that this cam here is spinning, and I'm trying to, there's going to be a spring here, the valve spring. And I want to make sure the spring is stiff enough such that the contact is maintained, that this blue thing doesn't launch off of the cam as it's rotating. I want to make sure the spring is stiff enough to keep those engaged with one another. So we're going to use SOLIDWORKS motion to evaluate that type of thing. So our last one for today is this guy here. We're going to run a quick little motion study on it. So to begin, where is our motion tool? How do I run a motion study on this? Well, go right up to those same add-ins. Okay, got SOLIDWORKS motion listed right along there. I'll go ahead and click that button, turn that on, and wait a moment. Okay, takes a moment to boot that add-in up. Once that's booted up, then you won't see anything pop up though. You won't see like a motion tab or anything like that. Okay, you won't be able to tell really, but until we get down into the actual interface. If I go to the Assembly tab, I can use this to create a new motion study, which I could have did without turning on that add-in. Okay, but if I create a new motion study, it creates a study down here. And here is where motion analysis, this is what that add-in did for me. It enabled this tool here. I would not have seen this motion analysis here otherwise. So I'm going to go ahead and click on motion analysis. Okay. And another thing I'm going to do that I do with all new motion studies I create, I'm going to disable the playback of view keys. Okay, this allows you to kind of rotate, pan, and zoom around your model. You can set up like different camera views, but if you don't plan on using those camera views, you might as well just turn this off for now. And then what we'll do is let's set up a motor, put this thing spinning, and set up some of the contacts in the spring. So we'll start with our motor. Apply a motor onto this guy here. I'll spin it around. I want it to rotate this way because that's kind of the way my cursor's been moving this whole time. And this thing's gonna be moving pretty quick because this valve is for like an engine. So I'm gonna do 1,000 RPM. 1,000 RPM. Okay. And let's test that out. Let's see what 1,000 RPM looks like at our 5-second. Looks like a 5-second time scale. If I hit calculate, that looks a little funny. Okay, it's just kind of flickering at me. Okay, so what's wrong there? Well, at that time scale, we need to adjust the frame rate and change the time a little bit. So I'm going to go into my motion study properties, my motion settings. So this little toolbar here has a lot of the things I'm going to be using. Okay, one of them this motion study properties here. And I'm going to bump the frame rate up so we get a much smoother animation. I'm going to use like something like 2,000 frames a second. You might just kind of trial and error it, figure out what works for you. Okay, bump that frame rate up, and now if I hit this little calculator button, okay, that looks now looks a lot smoother. Okay, still need to turn on contact and all that kind of stuff, of course. But now look how long I'm having to wait for it to run that whole 5 seconds. I don't like that. Let me go ahead and stop. And I'm going to scale this back, or I'm going to edit it. I'm going to edit the key point time and make it 0.12 seconds. Okay, and now if I do a zoom to fit down here, now if I go ahead and hit calculate, it says, hey, I'm going to adjust this playback so it doesn't play back in 0.12 seconds, otherwise you won't see what's going on. It's going to take 5 full seconds to play it back. So now if I play it back, there's that 0.12 seconds spread out over 5 seconds. That's where this little interval here is set to automatically. Okay. So next what we'll do, let's add our contact. That's this button here. It actually looks like a cam with a follower on it, kind of like what we got going on here. Okay, it's a little contact button. And I'll select all 3 of these parts. You can divide them up into groups, and usually you get better performance if you use this contact groups tool. But for now, we'll keep it simple. There's only 3 bodies, so. And I'm going to make these steel dry. And depending on what you select here for the material, you see these, there's properties down here, like a stiffness, material stiffness, and friction coefficients. As I change these, like steel dry to steel dry, you see that number change, these numbers. That changes the contact behavior, the collision behavior between those components. Okay. So I've just set up all the contact, and is that all we need to do? Let me go ahead and calculate again. Let's see what it looks like. Oops, what are we missing? The spring. So let's go back to 0 here. Let's add that spring in. We go down to spring in next. So the spring will be between, if I select this circular edge, it'll use the center of that circle for one location for my spring. And if I select this rectangular face, or that edge could have worked too, it'll use the centroid of that face, which also happens to be in the center. So there's a nice spring. Now the spring, this is just a graphical appearance of a spring. Now the real numbers, the hard numbers you need to key in are over here. The stiffness of the spring, which I'm going to make something kind of small, 0.1. And then the free length, I'm going to make it a little longer so the spring starts out compressed. And now let's see how this works this time around. Let's go ahead and calculate it. And look at that. It stays together. Okay, play it back. I think it's staying together, right? Can you tell if it's lifting off or if it's launching at all? Now, if it's hard to tell, you could slow down the playback, add more frames per second, or we can look at some of our results. If we look at the contact force, as long as that contact force never hits 0, then that tells me they're maintaining contact. So if I look at those contact forces using this results and plots tool, we can go to forces, contact force, magnitude. There's a lot of options in here for different kinds of results you can look at. Kind of see all these categories and subcategories. But in this case, contact force, between these 2 parts, and you can select any face of the 2 parts, really just selecting the 2 bodies, and then you turn on the show vector and graphics area. That way it'll show a little yellow arrow for us. And there it is. Let me go ahead and just show you. If I play it back, you see the yellow arrow up there. It flickers a lot because I don't know, something about the frames, how it plays. But it looks really choppy to me. You know, look how choppy that is. Well, the way contact works in motion, it's a bit like a beach ball on water where the 2 bodies are allowed to interfere a little bit, like pushing a beach ball into the water, or it kind of interferes with the plane of the water. And so we're seeing that the 2 bodies kind of interfere with each other and they're recoiling a bunch, and it could be also due to precision of the contact. If I go to the settings, if I go back to those settings, we have a contact precision here, which adjusts in the background. There's sort of a mesh size that we use on the components to establish where things are overlapping or touching. You can make that mesh finer, or if I just try and use precise contact, that'll tell it to use the actual surfaces, the parametrics of those surfaces. And now if I recalculate it, it may take a little longer to run. Okay. Actually wasn't too bad here. But some analyses, I mean, they can take way longer to run if you do that. But now look how smooth it is. We do get little blips here and here, but you know, as it's trying to lift that follower up. And you can see for the most part, the contact never hits zero. Okay, we get a little blip there, but it's not like a long extended zero where it's launched off the surface. Okay, so I think this looks okay. But what happens if we use a faster speed? If I bump this up to 2,000 RPM and calculate it at twice the speed, crank this thing around at 2,000 RPM, maybe you can already tell visually that it's lifting off. I think I can tell there, right? But if you couldn't tell when you were watching that, if I show that plot again and adjust the scale, and go back to the scale, change it 0 to 10, 1 and I don't know, 0.5. There you can see 0. Yeah, there is a period of time where it sits at 0 contact force, and it's, if I click in one of these regions, I can see there it is. Yeah, it's definitely not making contact anymore. So I think that if it was moving at 2,000 RPM, we need to change our spring. Notice how I'm editing these things? I like to double click on the key to edit them rather than use the right click edit feature. Okay, this works, but you have to be careful about where your time bar is at. So just warning you, you may want to double click keys to edit things. Anyway, I'll do 1 Newton per millimeter, make it 10 times stiffer. Made that spring 10 times stiffer. And now it should maintain contact, I hope. And I think so. I think it looks good. But just to be sure, we'll look at that that force plot. I'll have to adjust that scale one more time. Just make everything 10 times bigger. And yeah, looks smooth and very consistent too. This time, not a whole lot of chattering going on. Very stable looking result after those 4 repetitions. All right, so that is a simple motion study. I guess there was one other thing I want to mention about it. Now, the reason why this was so simple is because the mates were already set up for me. That can be one of the most challenging things to running a motion study, is just get your assembly mates right. Okay, you don't want to have thousands of mates in here that the motion study has to solve all the mates for. You may want to group your components up a bit and just have the things that are moving be the only real mates between components that you have in here. Okay, so you know, this model here, this could be a big complicated subassembly of 100 components, and as long as they're all grouped into one subassembly, motion won't care about the mates for this subassembly. Okay, so we want to group things together, have nice clean mates, and that'll make your motion studies a lot easier to get started with. All right, so with that, showed you a quick motion study, how to get started with that. If you want to learn more about some of these tools, we mentioned this tutorials. You can go to your tutorials list under the help pull down. Again, they changed the location of the help pull down on the newer versions, where it's, instead of being on the left, it's on the right. But if you find that help pull down, go to the SOLIDWORKS tutorials, and you'll find a lot of the simulation tutorials already built in there. We also offer AMS sessions. Okay, if you contact our tech support with questions and how-tos, you can many times you can schedule a call with a GoEngineer representative. Maybe it usually lasts an hour, where we can work with you one-on-one on some of your design challenges. Also help get you started with simulation. If this roughly hour webinar didn't get you started, we can continue with this. And then we do offer full online training and also in-class training. You know, once things get back in the classroom here. But our course catalog on our website. Go to goengineer.com. and you can check out our available courses on there. So thanks again for coming, everybody.